And so it begins. Week 10, day 3. Start the timer. It's 12:02. Let's do this. ELO. Boom. See how quickly we can implement this. Who wants to be my partner for this? Main.cc, and I'll call this elo.cc. I need to change my include set. Include read.h. Who wants to be my partner? Somebody give me a working elo function and give me a working class. Just grab the class here then. So who's got a working elo? Did you guys finish? All right. Let's find out.
When I saw at least, at the most, I think they passed up to 9.
Mm-hmm. Who's got a working elo function? This is the wild world of sports. Main.ccl. I guess I'll grab my own. I'll be my own partner. There we go. POW is not defined, so we'll come up here and include CNAF. Actually, let's see here. What did I give you? I gave you lots of stuff to start with. Yeah, it's so easy. Okay, let's do that then. Copy name.cc up into elo.cc. cd them elo.cc. So grab some working algebra. Then name.cc or copy. Nobody wanted me by partner. I'll be my own partner. Okay. So you can only pass 19. So close. We'll talk about why that's slow in a second. So include data.h. I don't need you. Let's just include public read.h. Okay. So here we go. 12:05. Let's begin. Start the timer. I'm not going to use a deck. Not going to use a vector. Maybe I'll use an unordered map. I am going to use a set because that's what you guys are using. So we'll do that. Algorithm we might need. CC type, maybe. I don't know. Whatever. I'll leave them. So my partner just gave me the ELO calculations. Yeah, all that's done. Cool. Phase 1, inner name, get line, name, competitor C. So I need that class again. Okay. Then temp.cc. Competitor class there. There we go. So the competitor class is just a pods name, address, ID, elo, and it will sort based on elo. Now let's not do that. Let's do sorting on ID. ID is less than rhs.id. There we go. That will sort the binary search tree based on ID. By ID. Cool. All right, so now we can stuff this into a binary search tree, easy peasy. So we are coming down here, change the elo calculation. That's already been done by my partner, i.e. me. So all that's done. So we come down here, we make a competitor. That's all done. Check if it's in the data structure already. If so, die. So we need a data structure. And so the choice of the data structure is a good one. And the choice of your data structure is going to determine if you pass to the test cases or not. So I'm going to make a set of competitors named binary search tree. So we're going to come down here and we want to see, okay, so the user just typed in, here's a new person. We need to see if their ID is in the system already. Okay, we can do that using count. So if bst.count c die. Cool, done. If they're in the system already, it'll die. If it's not, it won't die. Otherwise, store it into the data structure. Cool. bst.insert c. All right. Cool. Easy peasy, 2 lines of code. All right, moving on. If the number of contestants is less than 2, die. So if bst.size is less than 2, can't have any competitions there. Very boring chess tournament. I have won martial arts tournaments before by being the only person in the N-up category. Do you guys know what the N-up category is? That's when your weight is and up. They'll have lightweight, featherweight, bantamweight, blah, 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 blah. And then there's the and up category. Whatever the top weight category is, that's the and up category. And sometimes I'd be the only person in it, which is nice. It's easy victory. All right. All right, so this is done. So we're going to get a line, and it gets an ID, if they're the same ID, it will quit. If it's lost or die, it quits. Okay. You check to see if ID 1 and ID 2 are in our data structure. If not, die. If they are, then pull them out. Okay. So if bst.count, let's use find in this case. So auto iterator 1 equals bst.find, and we're going to try and find C. And does it need, what does it need? It needs beginning and end. bst dot, was it? It's not, is it not find? Is it search? It is find, right? Okay, find. There's 3 overloads. Does it need a range? bst dot begin, bst dot end, and why do you not like me? No matching member function call for find.
Oh, did you do the overload yet?
There's BST, it's a set. Okay. Did I do the overload on what?
The operator overload doesn't need it to be
Should
fine.
be. No matching member function of call to find.
Well, get rid of the iterators. Should just be that.
No viable
That
member function.
should work fine.
It's because C is not a competitor. C is a character. That's why. Okay. Good job, Kearney. Up here, C is a competitor. Down there, C is a char. Okay. All right. All right. So, yeah. All right. Fair enough. Okay. Wonderful job there, Kearney. All right. So we're going to make a character. So I can't call it C. Damn it. Character. What's the name of my class again? Competitor. Competitor named com is equal to what is the order of the parameters? It's like name, address, something like that. Name, address, ID 1, and ELO, right? Something like that. Is that the order? Name, address, ID, ELO. Good. All right. Name, address, ID, ELO. So I'm just going to make a competitor like that. And that works. Cool. And then we will do the same thing with the second ID. ID 2. Like that. Do you approve, Amelia?
Yes.
Okay. So if either of them are not in the data structure, we need to die. So if the first iterator 1 equals bst.end, then we die. Otherwise, if it's not in the data structure for the second one, we die. Cool. All right. If they are, we pull out their ELO scores. So ELO 1 is equal to iterator 1 points to ELO. ELO 2 is equal to iterator 2 points to ELO.
But sir, are you sorting by ID or ELO?
ID.
Oh.
Yeah.
We already changed it.
Yeah, don't sort by ELO. It's a terrible
Yeah,
idea.
it is by default, so a lot of people were doing that.
Yeah, don't trust me, man. You gotta change it. Okay. So all right. So it's a learning experience. It's a learning experience. Both players have an ELO over 2400. Use k equals 10. Otherwise, k equals 15. So k is equal to 15. If ELO 1 is greater than or equal to 2400, and ELO 2 is greater than or equal to 2400, then k is equal to 10. That's how many points are up for grabs, kind of. Change ELO. Boom. All right. So final bit. Update the database to reflect the new ELO scores. All right. So a couple different ways we could do that. We got an iterator already. So easiest, simplest way is to make the ELO score mutable. Down to the bottom. That will allow us to just use the iterator to update it. So we got change here. And the change is the change in the first person. So we say iterator 1 points to ELO plus equals change. Iterator 2 ELO minus equals change. And we're done with that. And then finally, we just need to find the winner. And so there's a couple different ways we can do that. We will just use a range case for loop. Why not? For every const competitor by reference named C, because I can use C again. In the binary search tree, if C's ELO is bigger than winner's ELO should default to 0. Good. Okay. Then winner is equal to C, and we are done. So that was 8 minutes. Okay. I did cheat by being my own partner. So let's just move the a.out that I just built into here, an input tester, and see if it is in fact correct. Damn it. All right. Is my ELO calculation right? How's my ELO? My partner failed me. Look at this. What's going on here?
Yeah, what a horrible partner. I bet he forgot to use round or something.
Oh my gosh. What's going on here? How is that the bug? All right. Vim ELO.cc. All right, let's take a look at this. All right. ELO 1, ELO 2, K result. Powers, vault, difference, round.
That's correct.
Yeah.
Oh, that's fine. It's probably just you.
Oh, I have to vet the ELOs. That's fine.
Yeah.
Okay. ELO 1, ELO 2. I don't have any vetting going on here. Okay, that's fine. See, my first partner is supposed to write this stuff. I don't have a first partner. Okay, so if ELO 1 is less than 100, die. Like Thanos, I must do it myself. Fine. 100, die. That must be between 30 and 50. If K is less than 3 or K is greater than 50, die. Win, loss, or draw, it must be either W, L, or D. If C is not equal to W and C is not equal to L and C is not equal to D, die. All right. All right. Now it should be good. Copy the a.out from the home directory into here, run the input tester. Out of 20. 8 minutes. 11 if you count me doing the other partner's work. So how would you find the winner without going through a loop? I would keep track of the highest ELO score as you go along. Every time you do a match, you can write down who the highest elo is. And every time you enter into the database, you can write down who the highest elo is. The only trouble with that, I did it that way. It did shave about 0.2 seconds off my running time. But doing it that way, the only trouble is if you lose elo, then you have to invalidate the old winner. Right? So there's a little bit of trickiness where you have to check to see, did the top person just lose elo? And if they did, then you have to reassess. So it can be when it drops, then you have to go through the whole thing anyway. It ended up being too much of a hassle to worry about it, so I ended up just using a for loop. It was 0.2 seconds on a million elements, not the end of the world. So let's see, time it. So if you guys run time it, it will tell you how long your implementation is. So by my binary search tree implementation that I just wrote in 8 minutes is 2 seconds to process input file 19. Word count by line, input file 19. What is that? No, it's more than a million. It's 2 million lines of input. So I don't know how many actual things it is. Pretty big input file. So you could make the last thing faster. The trouble is, like I said, if the previous winner drops and the new winner is somewhere else in the data structure, then you have to do the loop anyway. So it was too annoying to work with, so I dropped it. Okay, so running time 2 seconds. How many people beat 2 seconds on the running time? Arrow of the Hills says I was able to do it in 1.5 hours. Is that running time of your program, or is that the programming time? Is it your time, or is it the running time? Because it could be either. If you use vectors, you could use vectors. You are going to fail 18 and 19 if you use vectors. Also, if you have any order in operations when they should be login, you will fail 18 and 19. Okay. The reason for that being, this is punishment for not understanding Big O, right? So anytime you're looping over the entire array when you should just be doing a binary search, that will penalize. Like I made these test cases exactly the right size so that if you used a binary search tree, you would come under the threshold and get the point. And if you used any order in operations when it should be login, you'll fail it. That was a deliberate, very tricky thing that I did on this homework assignment. Not tricky, but enough to make you guys think about Big O. Like this is not some theoretical, algebraic thing. It's like it makes a huge difference in terms of runtime. Doing 1 million times 1 million operations is 1 trillion operations. Doing login operations is 20 million. 20 million versus 1 trillion. It's a huge difference in runtime. Huge difference in runtime. 50,000 times 2 seconds is 50,000 times 2 seconds, minutes, hours. It's over a day. So if I had used vectors for this, let's say, my running time would probably be over a day. Instead, it's 2 seconds. That's why Big O is so important. Okay? So if using BST, don't use a range-based for loop if you're searching by what it's sorted by. Yeah. If you're searching for somebody by ID, this is called a key, right? You're searching by a key. As long as you're searching for the ID, it'll be fast. If you have to search for something that's not the key, like the ELO, then it'll be order in. Okay. I counted 100,000 lines before I exited the file. Literally held page down. Shift G. Yeah, it's too much. Yeah, word count. WC-L. Word count by lines. If you do word count by itself on input file 19, it tells you lines, words, and characters. Let's see if it has a human readable. No human readable. Some of these things will allow human readable, which will put things in, Ks and things like that instead of big numbers. disk usage -k, disk usage -k, human readable. See the difference? 33 megs in the current directory instead of 33212. Okay, so that was your assignment. You guys had 2 days to do that. The reason why I gave this assignment to you was to see if you could use the standard library and code something up. That's the level of proficiency you need to be aiming towards. It doesn't have to be 8 minutes. Like I said, I do this in class, and normally you'd have an hour and a half to do it. But you need to, and working with a partner also helps, because you can have one person hashing out the algebra side of things and doing part 1, those if statements, and then the other person is doing the data structure stuff. So are they going to learn how to auto-generate test cases like you did, maybe for the data structure speed assignment? Yeah, I think so. So we will do a benchmarking test. The new server is almost ready to go. Probably over spring break, I will give you a benchmarking assignment. You can sit there and hammer the server, the new server, and see how that goes. All right, so I have not graded the ELO assignment yet, so I'll grade it, I don't know, 2:30, something like that. So, you know. So if you're planning on using your last chance on it, I would just fix it in the 2 hours you have right now. I'm giving you. All right. The new one's not going to be FizzBuzz. It'll be doing Qs. But it's actually when I would normally teach a couple weeks ago. But I've been waiting for the new server to come online so we can hammer it and see how it works out. Okay. So that is when you're working with a standard library, it's that easy. You can insert things into it. You can search things with it using find, or if you just need to know if it's in there or not, use count. And you can delete things from it using erase. The only one bit that might be a little bit advanced would be making this mutable. I made this mutable because, like I said, normally a binary search tree, you can't change any of the number of variables in it. And so you would have to call erase and then update the ELO and then reinsert it. So that's doing 2 login operations instead of 1. And so if you make the thing mutable, then you can just say that. That. So if you've got an iterator pointing at an element in the binary search tree, normally you can't do this because it's const. But if you make the member variable mutable, it works fine. And it won't break anything because we're not sorting on ELO. If you are sorting on ELO, this is going to break your binary search tree and horrible things will happen to you. Leopards will emerge from the walls and spiders from Australia will appear around you. So make sure that you are sorting based on ID, not based on ELO. Okay. Take by the ball and get a 19 out of 20. Changing from vector to BST would be painful, would it? I don't think so. I mean, maybe. I mean, I don't think so. Okay. You know, your tools are insert, find, count, erase. That's it. So, I, however, let's see if we can beat 2 seconds. What do you guys think? Cool, 1.4 seconds. Neat. That was fast. This is why Muyo was saying, you're just doing this assignment to flex on your students. No. I'm doing this assignment so you guys can see that if you understand the standard library, you can code. This is like a full program, right? This is like an actual thing that people would maybe pay you money to do, right? And you can code the thing quickly, right? There's a little bit of business logic, for computing the ELOs and stuff like that. Most of the work though is spent doing the input processing. You're reading in a ton of data from disk, and then you're doing all of this computation, your data processing, and you're going to output a result. And that is a classic pattern that you will see over and over again in computer science. And so, like, let's say you work for, like, Fort Washington Country Club, and they need somebody to compute tournament brackets or something like that. You know, where the first seeded person is matched with the last seeded person, and they have to punch in all the wins and losses in match play and adjust the rankings using ELO or some other system. Like, you should be able to code that up pretty quickly. You know, and if you're not there yet, that's why I'm doing these assignments. These assignments are not here to punish you. They're not here to be punitive. They're here to get you in the groove of being able to make real programs that are doing real, like, that's millions of lines of input, right? It's not like 3 people, you know, it's millions of lines of input. And you can, and this is to teach you big O, right? Like 2 seconds versus 27 hours, right? It's a pretty big difference, right? Just from a couple lines of code changing. A couple lines of code, and you can go from 27 hours to 2 seconds. Okay. Still mad that Florida beat Virginia Tech in overtime. There goes my perfect bracket. You got it faster than 2 seconds. I'm almost faster than 2 seconds, yeah. So, how is your code almost faster than 2 seconds? Arrow. So how did I get it faster than 2 seconds? Well, I didn't use a set. How did I get it faster? I used an unordered map. So I could have used a set. Sets are not bad, right? So a set would do everything in order login time, right? Login, insert, search, and erase, right? Pretty fast. If you have 1 million people in your chess tournament, it's pretty fast. 20 steps to find any person. It's pretty fast. A deck, what would be the running time to find a person with a certain ID out of a deck in big O terms? So if I've got a deck that just has all the people in my chess tournament in it, their name, address, ID, and ELO, and I'm trying to find the person with the matching ELO, how many steps is that going to be? 1, log in, or in? Do you have any money writing on that as Scandid? What is it? Order what? You guys still here? Is your confidence crushed by the assignment? It shouldn't be. You should get excited. You should get excited by how quickly you can write code if you know the standard library. So if we don't have a sorted deck, if we don't have a sorted vector, then the only way to find somebody based on their ID is to start at the beginning and go to the end. So what big O is that? If you have to start at the beginning and go to the end of a vector or a deck, what big O is that? Yeah, let's order in. All right. A map is also a binary search tree. A little different. We could probably talk about it today. Search. Erase. This is a BST. That's also BST. So, unordered map is order 1. Insert, search, erase. So that's how I was able to get an even faster. Even faster. Pretty good. It's pretty good. Order 1. Yep. So that was cool. But you know, Muya's like, you're just doing that to. I'm doing this to show you guys, you know, the benefit of Big O. You know, by going from a vector to a set, you can go from 27 hours to 2 seconds. And by going from a set to an unordered map, you can go from 2 seconds to 1.4 seconds. Right? So it's a comparatively smaller jump, right? But, and probably honestly, the reason why it's still taking 1.2 seconds is because you just got to read in all that data, right? Like, you're just processing millions of lines of code. It's going to, like, you're probably I/O bound at that point. The unordered map at that point is no longer this isn't even the bottleneck anymore. And that's only 0.8 of the 2 seconds, right? So, probably 1.2 seconds are just spent reading from hard drive. Can I just change set to unordered map? No. So we need to talk about maps first, then we can talk about unordered maps. Okay, so that's our topic for today. We're going to talk about maps. Because we're still on the BST section of our class, and your next homework assignment is going to be doing a BST, but you get to do it this time instead of me. Okay, so remember, after class is over, I will give you 1 more hour to do ELO. Don't drop out now. You should be able to do it. Don't sort it based on ELO. Right. Sort it based on ID if you're using a set. Okay. So what is a map? What is a map? Okay. So I already have a map. Damn it. Move star.cc to make your old code. Move star.cc to old code. There we go. Clean up my directory a little bit. Move star.h into old code. Remove file.txt. Remove star.targzip files. There we go. Oh my gosh. Polkadum.txt. What is that? Remove point.s, remove heroes.txt, remove polkadum. What is that? What is foo? I don't know. Remove applesauce, remove Black Friday. Remove Bob. Take that out. All right, cleaned up a little bit. All right. So let's learn about maps. What is the difference between a map and a set? Really? Okay, thank you. So a set and a map are very similar. They're both BSTs. Okay. So their big O running time is going to be the same. Therefore, their big O times are the same. So what's the difference? The difference is with a set, you have to have an operator less than or some other comparator function, usually it's the operator less than, to sort it. With a map, you provide a key to sort it. Huh? What does that mean? Okay, well, so let's make a person. Let's make it a struct, whatever. Do as I say, not as I do. String name, long SSN. Okay, so what else do we have? Address. Let's create like a. What else can we have on a person? What other things can we know about a person? Phone number. So you taught us to do a BST on an assignment wasn't optimal. It was optimal enough to pass all the test cases. I specifically chose BSTs because BST was enough to do it in 2 seconds if you didn't screw up any of the operations. If you screwed up any of the operations, like instead of doing a find, you did a range-based for loop. A range-based for loop is order in. A find is order login. If you screwed, I did it specifically so that if you did the wrong running time, you did a slower running time for any of them, then it would exceed the 3-second time limit. So that's your answer, Yoxslammer. It's not to flex on you guys. It's to teach you about Big O and to teach you how to use the standard library and stuff like that. How to whip out code quickly. Coding competitions are a great way of learning to program. They do teach you some bad habits, but being able to knock out a program in 8 minutes is really useful. And employers like employees, they can do work quickly, you know. So we'll probably do another 1 or maybe 2 of these coding competitions before the end of the semester, because you need to be able to whip out solutions. You got bamboozled. Yeah. BSTs would make you pass that in a 3-second time limit versus my vector that would take hours. Yeah, exactly. Because it's comfortable. Vectors are comfortable. We know vectors, right? We've been doing them for like almost an entire year now. You know, it's like you can pass the test cases if there wasn't a giant million-line one, right? So to motivate you to use a binary search tree, I had to make a very carefully crafted data set that was big enough but not too big, and you know, there was some thought that went into that. Okay, so here we got a person, and so with a map there is a concept of key and value. So a key is what you use to search a data structure with. A value is the whole object. Name, address, etc. In this case, the key is going to be SSN. Have you guys ever wondered why Social Security numbers are used everywhere? Caps. Keys must be unique. Does this have anything to do with the APIs using API keys? Not exactly. Not really. Keys must be unique. Keys are what you use to search a data structure on. And so the reason why Social Security numbers are used everywhere is because it's the only thing in America that we have that each person has a unique number, right? 2 people could share an address. 2 people can easily share a name. 2 people can have the same phone number. The only thing in America that each person has uniquely is an SSN. Okay, and that's why they use Social Security numbers. That's why identity fraud is such a problem, because you can't revoke your SSN. Because every database in the universe, you know, will use your SSN as the key to find you. You know. So yeah. All right. So at our school we have an ID, like my student ID. My student ID number 0712 whatever. Fulfills the same purpose. That is what they use to look you up in the database. Okay. And so the key can be part of the value, right? In this case, the key is part of the value. It doesn't have to be, but it usually is. And so that is what we're going to be doing. So what does it look like? Okay, so let's make a map of persons called BST again. Why not? Because it is a binary search tree. So let's do this. While... What's wrong with that? Right. It needs the key type. So CPP reference map. Usually implemented using BSTs. Red block trees are a type of red-black trees are a self-balancing binary search tree. Like I said, this is a junior level data structure. There. So it takes the key and the value. Let's see here. Key first, value second. Okay, that's what I was looking at. So that. Okay. Well, true. Has 0 chill. All right. Well, true. Let's just read people into the binary search tree and see how it looks. It'll look a little bit different from before. So before we needed to have a member function here, right? We needed to have bool operator less than. Remember that? That's what the binary search tree would use to put it into the binary search tree. Here, what we're going to do is we're going to provide a long, and that's what it's going to use to put it into the binary search tree. That's the only difference. So what is that going to look like? String name equals read. Please enter a person's name. Done to be done. If name equals done, break. Otherwise, we are going to read in an address string YYP. Please enter person's address. That. And then SSN and phone. All right, YYPP. Long SSN. YYP and phone. I like lining everything up. I do that so that I can see typos more easily. So that should be good. So now we're going to make a person out of those 4 things. We can say person P is equal to name, address, social security, and phone. So that's going to create a new variable named P of type person, and P's name is going to be set to be name, and P's address is going to be set to be address, and P's SN, so on and so forth. Now we need to add them to the map. So we do it like this. BST dot insert. You can use square brackets, but I don't recommend it. Don't use square brackets. You'll see that used all over the place. The trouble with that is if you can use square brackets to look up to see if something's in the data structure. But if it's not in the data structure, it makes one. So don't. Let's look at insert. This way works also. Let's look at insert. So you'll notice that insert takes a pair. Okay, it takes a pair, and it's going to take a key, and it's going to take a value. So we're going to insert the key, which is SSN. We're going to insert the value, which is P. You guys see that? So rather than having an operator less than that is using to sort the binary search tree, instead what we do is we provide a key, and that key is what is used to place it in the binary search tree. So it's going to use this number here, and that will be what it uses to put it in place. Okay? And so every time we access this person, we access it by providing a social security number. So we provide a social security number, and we can add it. We can provide a social security number and search it. So for example, if we wanted to see if the person was in the database before, we could say if bst.count, and we just pass in the SSN. If bst.count is true, that means they're in there. Then cout error person with SSN equal to SSN is already in the database. Note that it's not looking at the name, it's not looking at the address, it's not looking at the phone number. If there's somebody with the same social security number, it will fail. And then we'll just continue. So it will jump back up to the top and re-enter. Okay, so this is very similar to what we had before, except rather than it using the less than operator, every time you work with a binary search tree that's a map, you provide the key, and in this case, social security number. And it will insert using the key, it'll search using the key, it'll delete using the key. Okay. Is this Intuit? Our social security is like 9 digits. Yeah. Okay. So.
Apparently, the teachers have gotten a point on the scoreboard.
Huh? Scoreboard. Good job. Good job, teachers. Show those students what's what. It's always funny when they have like student versus teacher basketball games. You've got like these 5th graders getting dunked on by basketball coaches and stuff like that. So.
She was explaining what we use corners for, and we missed one thing.
Eddie, can you turn the light on behind me?
Okay.
Thanks. It'll make it a little easier for the students to see me. All right. So that is how you build that. And if we were to delete using it, yeah, we could delete this way. Deleting. So if you type it in again, it'll delete it. bst.erase, passing a social security number. So if you type the social security number in twice, it'll erase it. I don't know. Doesn't make sense to me. But I just want to show you guys insert, search, and erase. Okay. Now, if you were to find if you wanted to search using find, not just count will tell you if it's in the database or not. But if you wanted to use find, there is a twist. And the twist is with maps, it's always pairs. Okay. So when you insert into a binary search tree, it takes 2 things. It takes the key that's used to place it in the tree, and it takes the actual data that gets written in. When you search, you get 2 things back out. You get the key, which technically you don't need because you've searched on the key. But you get the key and the value back out. So let me show you what that looks like. So string, okay, different long SSN, read, please enter a SSN to search for. And so if we say auto iterator equals bst.find, passing the social security number, this is actually going to return a pair, or it's going to return an iterator to a pair. So if we just tried, so we have to do. So what is a pair? A pair, if you guys remember, is 2 things. It's dot first and dot second. Dot first is just going to be SSN again. So why it returns it, I don't know. We have access to it. So iterator points to second is going to be the person. That's going to be the record. That's the twist. That's what makes maps a little bit harder to use. Sets are easier, and if you have an operator minus, you don't have to go through all this rigmarole. But iterator points to second is a person. So I can say person P is equal to iterator points to second, and then I can see out p.name, p.address, p.social security number, p.phone. Person's name, Bill, address, 111 Main Street. Please don't egg my house. Ooh, please enter person's SSN. How did that break? It's interesting. Oh, it's because I'm reading a string. Yeah, I should be using getline right now. Rather than read, I should be using read line. Is there any time where you'd prefer using the set BST over the map BST? Yeah, you know, it's just nice having the operator less than do all the lifting for you, because it's kind of annoying working with pairs. Because you search for it and you get a pair back, and the first part of the pair, the dot first, is literally the thing that you search with. So if we were to see out iterator points to first, and we print out the key that we literally just searched for, that the user literally just typed in, should be the same thing. Bill at 111 Main Street. My social security number is 420-69-6666. Thank you, Shahab. How did you know my social security number? Person's phone number is 111-222-3333. And our person's name, Rente, address 987654321 Main Street. His social security number is 123-456-78910. And the phone number is 555-1212-1212. Okay. Done. 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 All right. So, oh, please enter the social security number to search for. Yeah. So, we should check to make sure that it's in the database, right? So if iterator equals bst.end, then we will print cout not found. Right. Else print all this stuff. Bill 1, my social security number is 123, my phone number is 123. Shahab, his address is 1, social security number is 222. His phone number is 999. Why is it not? Why is that not breaking? Like an extra space on that? What am I missing here, Malia?
Wish I could tell you. I'm actually really not sure.
done. But it moves on to the next line.
Okay, wait. Let me see it one more time.
But it's not printing the address after that. It's moving right on.
Yeah, it's just like the break. Maybe your read line is adding a \n to done. No, but then it would have \n.
That's why I'm printing those asterisks there. Okay, my brain hurts.
Yeah, that just doesn't make
Because
sense.
Oh no, it did work. It did work. It's now moving down. Okay, my gosh, everything works fine. Why should I doubt myself? My lord. Okay, yeah,
You can't even write code that doesn't work. So
I know, right? It's like my curse. Okay, so yeah, it was actually printing this line, and I was just I was thinking it was that line. Yeah, good times. All right, yeah, no, everything was fine. Everything was fine. Okay. All right. I was baffled there for a second. All right, so Bill 111, Main Street, SSN is 123, phone number is 555-999-1212, and we'll add Muya, which is address is 222 Main Street, SSN is 321, phone number 111-222-3323. Done. Now we're searching for an SSN. Okay. So if we search for 123, then you can see that the iterator returns the first part of the iterator. The pair that it returns is literally the key you just searched for, which is what we know it already. So yeah. So if you don't want to do that, you can use the square bracket, which is why the square bracket thing exists. So you could say like person P is equal to BST square bracket SSN, like that. But this is terrible, so you shouldn't use it. Even though you don't have to mess around with pairs anymore. What happens is that this, sure, if the social security number exists, it will return the person with that social security number. So it's searching for the key, and if it finds the person, it returns the person. Easy peasy. But if the person doesn't exist, what happens? It makes a person. What? Yeah, it makes a person. If the person doesn't exist with that social security number, it will make a person and put it into the data structure. So if you want to do that, you have to use count first to make sure it exists. And then if it exists, you can use square bracket. And so it's at a level of like, is it worth it at that point? Find is annoying because it returns a pair, it returns a key and a value. The first part is the thing that you search for, so you don't need it. It's completely unnecessary. It's literally the social security number you search for. And so what you always do is you just rip all the data out of the second part, and then you're good to go. So either way, there's like, so if you wanted to do it this way, you would say, let's see, if BST dot count SSN. So if the person exists, then now it's okay. So option 1, if you don't know if the SSN exists, using square bracket will create a new person, which makes no sense whatsoever. Okay. Option 2. So option 1, you first use count to see if they exist. And if they don't exist, else not found. Option 2, use find. Find returns an iterator. Notice how there's no iterators here. This is usually easier for students to work with. There's just a giant foot gun with this square bracket. If you search for a social security number and it's not in there, it will make a new person and insert it into the binary search tree. So you always have to pair it with count if you want to use this, if you want to avoid the iterators. So this code here, what does it do? It searches through the data structure we've created for somebody with that social security number. If it finds them, it returns a pointer to that node in the binary search tree. If it doesn't find it, it returns a pointer to end. And so you have to check to see if it's there anyway. Yeah. So the logic is, it's probably even less typing doing it that way. And then, yeah, I mean, technically we don't have to do that line there. So if the iterator is not pointing at the end, that means it's pointing at somewhere within the binary search tree. We grab it's a pointer to a pair. It's a pointer to a pair. So there's like 2 levels of indirection going on that causes students' faces to melt sometimes. So do I recommend using a set instead? I guess. I don't know. It's probably a little bit easier, actually, to use a set. But the nice thing about a map is that you don't actually have to have, it doesn't have to be sorted on a member variable. You could have some other key, right? So that was the only episode of Full Metal Alchemist I skipped with my daughter. Episode 2 of Brotherhood. So, yeah, if you're using a set, you would just do this instead. Bool operator less than const person p inside return SSN is less than I do 2 of them p dot SSN. So if you want to do a set, you just do that, and then it would look like this instead. Set of persons and BST2. Hashtag includes set. And so what is the difference between a map and a set? A map has the key and the value split. With a set, the value, the thing that you're inserting, the value, the database entry, the value you're inserting is also the key. That's the difference. And so with a map, sometimes the key is not going to be part of the value. And you need to do it that way. For example, you can map between strings and ints. So for example, if you wanted to have a map that held the days of the, how many days a month has, you would map between a string and an int. And so you could say January is equal to 31. February is equal to 28. Sometimes. March is equal to 31, right? And so with a map, you can map between a key and a value, and they don't have to be the same type. With a set, the thing that you're inserting is the key. The value you're inserting is the key. So it will just sort based on whatever operator less than you have to find. Okay. So yeah, a calendar, yeah. So that would look like this: map between a string and an int called calendar. You could say calendar janvier 31, February equals 28, leap year February equals 29, right? And so with a map, you can map between 2 different things. And so, and if you wanted to print out, like, see out January has calendar square bracket January days. Okay. So, yeah. Yeah, that's a good use for a map. Right? If I was doing this thing here, I'd probably just use the less than operator. Does this make sense to you guys? Looks like an array, huh? And so one name for this maps are sometimes called associative arrays. So the index doesn't need to be an int. So you can kind of think of this as an array where you don't have like array element 0, array element 1, array element 2. You have array element January, array element December, array element November. And you can just treat it as what's called an associative array that associates between a string and an int or something like that. So in a lot of programming languages, this is how they do arrays. Arrays aren't int indexed necessarily. If you do Lua, JavaScript, Python, you can just write into an array with index of Bob. Works fine. So January is the index. Yeah, it's the index of the array. So, and then the value, that's the key. The key is January. And the value is 31. So the key is used to access the value. And you will those vocabulary terms, by the way, are really important. Key and value. They come up all the time. If you ever do database stuff. Primary key. Things like that. Questions? It's binary search tree. They go running times the same. Balanced. It's a balanced binary search tree, guaranteed. This part's annoying. So when you're grabbing a class from a map, you just have to remember that. You have to remember it returns a pair. And you pull the second part of the pair out. That's your person you found. And everything else works the same. Or you can do that. You just have to be very cautious with the square brackets not to not search for something that doesn't exist in it. Why are maps so fast again? It's a BST. So you might be like, wait, I thought you were going to tell us about unordered maps. All right, cool. I got 20 minutes left. Let's do it. Unordered map is a thing? Good, it's a thing. Why do you flip out? Like it flips out. It's like, no. Oh wait, yeah, it's okay. That's fine. Okay. So here we have a map. Okay, this is a binary search tree, and it's going to put nodes into the binary search tree based on whatever number we provide as the key. In this case, it's going to be the social security number of the person, and so it's going to put people with a smaller social security number to the left. People with a bigger social security number are going to go to the right. You don't have to worry about that. All you have to know is that whatever key you provide, that's used to store. And if you ever search based on that key, it'll come back. Okay? It's like providing a password. You provide a password to save something, and then we provide that password again, it comes back out. Like a locker. I don't know. So, what is the running time on a map? So for this guy here, what is the running time for insert? What is the running time for search? What is the running time for delete? Seeing it says order 1, wrong. That's unordered map. In, login. It's a binary search tree. The answer for binary search trees is almost always going to be login. Inserting, searching, deleting are login. If you want to do something like printing a BST where you have to print everything, yeah, it's going to be order in. You guys shouldn't be guessing about this stuff. Like, you should just, know. But you don't know, and that's why you're taking this class, so it's okay. Please participate in the chat. You learn that way. I'll take attendance. There. Take attendance right in the middle of the class. So yeah, this is insert. It's going to be order, login, insert, search, and delete. Okay. Now, let's say I wanted to have more speed, but I'm going to lose the ability to sort. First of all, let's see what this looks like if we do a range-based for loop. So if I say for every person, for every const person p and bst, will this work? It's probably going to return a pair, isn't it? Yeah, it's going to return a pair. Conversion from pair. Yeah, this is actually going to be a pair. So const auto pair dot second. Okay. And then we will print. So let's print the BST out. Okay. So there's an important property of a binary search tree, which is that it's always sorted. It's really nice. If you need to, yeah, January 30 days, cool. So if I need to insert Blancas, then address of 111, Main Street, sorry for doxing you, social security number 111, phone of 111, and then we'll do sing with an address of 222, Main Street with an SSN of 222, and a phone of 222, and Yoxtheimer with an address of whatever, and a social security of whatever, and a phone number of whatever, and Kearney with an address of whatever. It runs on Main Street apparently, and stuff like that. When we're done, you will see that it is printing. It is sorting the. It needs spaces in there. Damn. Inline and inline. There we go. That'll look a little nicer. And let's even see out some dashes to make it look a little nicer. Try this one more time. Blancas 101 Main Street. Social Security, phone, Yoxtheimer 222 Main Street. Social Security number of 1, phone number of whatever, versus in Kearney, address, whatever, SSN of 1000, Muya, Main Street, Social Security number of 50, and we're done. So what it's going to do, it's going to sort. It's always going to be sorted based on the key. And the key in this case is the Social Security number. So Yoxtheimer will have the lowest one. You can see, sure enough, Yoxtheimer is the first person to be printed. Muya with a Social Security number of 50 is second. Me with a Social Security number of 1000 is third. And Blancas with a Social Security number of some big number is fourth. Okay? So a binary search tree is always sorted. That's a really nice property if you need it.
This is what I mean that I get like a free dog.
Uh-huh. Oh, nice. That's really cool. So, so do you guys understand? Like, this is why we use the binary search tree. If you need it to be sorted, if you need your stuff to always be sorted, which you need sometimes, then a binary search tree is great because it's always sorted. Now, what if you don't need that strong property? What if you don't need it to always be sorted? Like maybe I don't care what order people in the Social Security number database are held in. Why is it sorted by SSN again? Because that is the key. So, foreground. This is the map, and the social security number is used as the key. That is what it is sorting on. If I was using normal set, it would be sorting, again, on the social security number. That is what it's using to sort the people always. So the data structure is always sorted by a social security number. And sometimes that's what you want. Sometimes you need a data structure that is always held in sorted order because you're printing it out a lot or something like that. Or, you know, you always need the next person. Like, let's say you've got a bunch of timers that are going to go off, and you need to know when the next one's going to go off. Well, you want it always sorted by time that it's going to go off, and so you just grab that, and you don't have to go through the whole thing. So, so what if we don't need that property? What if we don't care that the database is holding everything in sorted order? Well, we can get more speed. And we get more speed by using something called an unordered map. So watch how hard this is going to be. It's going to be incredibly difficult for me to change all this stuff from order login time to order one time. So there's our old code, map long person BST. It's got login insert, login search, login delete. You guys should know this by now. You should know that on a binary search tree, to go through a binary search tree and find a node is log base to event. To search it, log base to event. To insert into it, log base to event. To delete from it, log base to event. You should know that by now. If I want to make it log one, or log one, no, order one, constant running time, will give you a dramatic increase, so 20 times faster on 1,000,000 elements. Observe. There we go. That's it. And if we want this binary search tree here, I probably shouldn't call it a binary search tree anymore because it ain't. It's not a binary search tree anymore at all. But if I have a set, same thing. Watch this. Unordered set. No, let's not worry about that for now. Okay. There you go. So now it's order one. So on 1,000,000 elements, it'll be 20 times faster. The only bug is that I shouldn't be calling it a BST anymore. Because it's not. But it's just a variable name, so who cares? Do you guys see that? Order login. Order one. Order login. Order one. That's it. This is why the standard template library is so amazing. You can switch back and forth between different data structures based on your needs. And that's it. I just made my code 20 times faster on 1,000,000 elements. So let's recompile it. What makes unordered map to be order one? Well, you got to learn a new data structure for that. And we're not going to have time to do it today. So for now, I will just show you Blanca's address is 101 Main Street. SN of 1,000. Kearney with an address of whatever. SSN of 1,000. Muya. SSN of 50. Wolf. SSN of 1. Done. So now when we print it out, you'll see they are no longer held in sorted order. Maybe they are actually. Look at that. Interesting. This is an unordered map now. Well, check that out. Doesn't have to be. Okay, the whole point of an unordered map. Did I type it in backwards order? Maybe that's why. Let's try this one. 1, 1, 1. Blanca's. 20,000, 20,000, 20,000. Kearney. 1999. 1999. And Malia. 50, 50, 50. Yeah, good. I think I just typed it in sorted order. So you can see it's in the order that they were inserted backwards, right? Okay. So they're no longer sorted by Social Security number. So if you don't need it to be sorted in Social Security number, then you use an unordered map. Simple as that. Okay. So that is the rule for today. If you don't care if the thing is always sorted, then use an unordered map instead for speed. It's a hash table. We'll learn hash tables next. It's our next data structure. But we're still in binary search tree mode. So what's your next homework assignment? You're going to have a week to do it. It'll be due next Friday. And it is called Dungeon Delve. So sudo deploy homework csci 41 dungeon delve. And for this homework assignment, you are going to have to write a binary search tree. You cannot use the set class. I mean, you technically could. It won't help you solve the problem, though. So you thought a map is a hash table? Nope. A map is a binary search tree. A unordered map is a hash table. So for Dungeon Delve, what you are going to do is you are going to make a dungeon solver. So if you remember that presentation I gave you guys when we first introduced binary search trees with the Daggerfall music in it. Let's see. Dun 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 dun. Oh. Dun 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 dun. So what you're going to be given is you're going to be given, first of all, a dungeon, and then you're going to be given a passphrase to escape from the dungeon. And what you're going to be doing is you're going to write a program that solves the puzzle. And so given a dungeon, like for example, the dungeon might look like this. There's a M, P, and a O. And over here might be a G, and to the left of the G might be a B, and the left of the G might be an A. The right of the G is an I. Right, it's a binary tree. So all of the dungeons you'll be given are binary trees. It's based on that Dungeons & Dragons game I wrote 20 years ago that had a binary tree puzzle in it. Every letter to the left is smaller, every letter to the right is bigger. And so if you have to find the exit, E-X-I-T, then, and you're here at M, you have to go to the left, and okay, we're at G, go to the left, we're at B, go to the right, aha, here's E. And so what your code is going to get as input is two things. First of all, you're going to be given the dungeon as input, and you have to build a binary tree using the letters as they're given. So for example, the input might be M, G, N. So you insert M first, you insert G, that's to the left, you insert N to the right, you're maybe then P, P's to the right of N, maybe you're given O, O's to the right of M, and so you're going to build a binary tree first. So you're given a dungeon first, and then you're given a passphrase, exit, or whatever. And what you're going to output is take the left door, take the left door, take the right door, hit the button, retrace your steps to the start. And then X, I don't know, be down here somewhere. Take the right door, take the right door, take the right door, hit the button, retrace your steps. For I, take the left door, take the right door, retrace your steps. For the T, I don't know where the T would be, somewhere over here, take the right door, take the right door, hit the button, leave the dungeon. That's it. You guys are going to have a week to do that. And so you don't have to implement binary search tree delete. Yay, there's no deleting. There's only inserting and searching, and those two things are pretty easy. And there's already example code on how to do that in /public/bst. So all you have to do is build a binary search tree using these letters. You're going to build a binary search tree of chars, Each time you insert, you start at the root, and if the root's available, you insert to the root. If not, if it's smaller, you go to the left. If the left is available, you insert there. If it's not, you go to the left. And so all you have to do is insert into a binary search tree and search a binary search tree, and that's it. You guys got a week to do that. So no deleting. Deleting's annoying. That's it. That's your homework. So good news is you guys won't die doing this. Blanca's like, I died immediately. Yeah. So that's your homework. It's not too bad, I don't think. And this will give you experience working with pointers again, and you'll understand binary search trees better, because once you implement a data structure, you kind of have a better mental model of what's going on. You're not going to guess anymore, like, what's the running time of this? I don't know, order 1, order in, order login. I don't know, I don't have it memorized. You don't need to memorize it. Like, you shouldn't need to memorize any of these things, right? It's, if you understand that a binary search tree has a number of levels equal to the log base 2 of the data, if it's balanced, then searching it, well, worst case, it's at the very bottom of the tree, so it takes log n steps to get there, and you can calculate it, right? You can recompute from your mental model of how a binary search tree works what the answers are. I don't have that table memorized. I just know how a binary search tree works. I know how a linked list works. I know how a vector works. I know how a hash table works. And so if you ever ask me, okay, what's the running time to find the max element of a vector? I'd be like, all right, you gotta start at the beginning, go to the end, order in. All right, what's the running time to find the max element from a sorted vector? Well, if it's sorted, then the last element is the max, so it's just order 1. And so you just think it through, and that's how computer science people are. Computer science people talk in terms of big O all the time. It's part of our vernacular. And the reason why I have you guys write these data structures is because then it helps you internalize and understand from the inside how a binary tree works. In practice, am I going to write my own binary tree? Hell no. I'm going to use set. Right? For this homework assignment, I was able to crack out that ELO assignment in 8 minutes because I just used the set class in the STL. I'm not going to write my own BST. Forget about it. If I have some need, like for this assignment, you actually have to write your own. You can't use the set class because it won't work. The set class is balanced, and so it'll rotate the things and it'll break the dungeon. So if you work hard, then you play hard. Get involved with intramural sports. Okay, so that's your homework, and and so in reality, you're going to be using the standard template library, but you need to not use the standard template library for this one because it won't work. A, and B, it'll help you learn how binary search trees work. All right, so that is that. Okay, have fun over the weekend. This will be next Friday. After that, you got spring break, and spring break will be a homework as well. All right, thanks, you guys. See you. It'll be fun. We're gonna hammer on a new server. It'll be great. If you hard, then you hard. Yeah, if you play hard, you work hard. Work hard.